Okay, now that we've gone through all the graphing, we're going to throw in one more section into here, which is actually an extremely important section. To me, quite honestly, one of the most important sections. And this is on optimization problems. Why do we care about calculus? Well, we've learned how to use the first derivative test and the second derivative test to find maximums and minimums. And that is one of, if not the most important things in the real world, is to maximize and minimize things. We've talked several times this semester about, for instance, profit is something that you want to maximize. Cost is not something you can minimize. Well, you can minimize it by not going into business, right? But average cost is something that you would minimize. What's the average cost per unit type thing? That's something you want to minimize. Okay, so real world application problems you want to maximize and minimize. You create a container, for instance, a soda can or a Tupperware storage container, or how about a can of soup? Why did they choose the size and shape that they chose? And I'll tell you right now, what they did was they wanted to minimize the amount of materials used to make that shape. And so when you look at these cans, you think, oh, they just made it into a cylinder. Well, no, it's a very specific cylinder that minimized the amount of material used to make that shape. Then you have people come out with things like Red Bull, who charge 4 times as much for poison, right? And they make it this awkward shape that doesn't fit like a normal standard can, and that's because they wanted to differentiate themselves. So they chose a path where they did not minimize the amount of material made to make the can whatsoever. But before that, it was pretty much standardized at everyone making the same shapes. So, optimization problems. We have this idea of wanting to maximize and minimize. How do we do it? So what are you going to do to solve optimization problems? I kind of wrote this up for you to give you some guidelines on strategies of what to do. This isn't exactly in the book. This is my interpretation of it, but we are going to be doing the problems in the book this time. So it says solving optimization problems. The first thing you want to do is determine the equation you want to maximize or minimize. And this will likely contain 2 variables. For instance, you might have the area of a rectangle. So the area is length times width. So you're likely going to have length times width, 2 separate variables here. It says determine the second area equation, which usually involves restrictions set in the problem. Solve this equation for one of the variables. So for instance, if you're doing length times width to find the area, you might have a restriction on, like maybe for a rectangle you're looking at fencing. In the fencing, you have a restriction on how much total fencing you have. So we know something about the relationship of length and width. So when you have that restriction, you're able to solve for one of the variables. You could solve for length in terms of width or width in terms of length. So what you do then is when you solve for one of the variables in terms of the others, you actually plug that back into your original equation. So now your original equation, like I've been talking about, area being length times width, now you would have it as length times, instead of width, you've already solved for width in terms of length. So now you have everything in terms of length. Now your original equation's in terms of one variable, and you want to maximize it. Well, how do you maximize it? First derivative or second derivative test. So find the first derivative, set it equal to 0 or undefined, and then you can, if it's easy, find the second derivative. If it's not, test your intervals. And think about what realistic numbers could be. Like you might get a negative number, so a length of negative 5 feet. Well, that makes no sense, so we don't even need to consider that. So think about what's realistic. And we're actually going to use the first derivative test or second derivative test not only to find the maximum or minimum, but remember that also proves that it is a maximum or minimum. So I have to see your work on this problem of either the first derivative test or the second derivative test to directly prove that this is the maximum or minimum. And it says that right here. It says use the first derivative test or second derivative test. This step is mandatory. This is where you are proving it is a maximum or minimum. And then the last thing you do is interpret the solution. Sometimes they want the length, sometimes they want the width, sometimes they want the area. So just make sure you go back and reread it and determine which exactly in this point, in this situation, did they want. Okay, So let's look at an example. Example 1, it says find the maximum volume. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. It says as shown in figure 4.54. What dimensions will produce a box with maximum volume? So we have two things that we want to do here. We want to maximize volume. And for volume in a box, it's always the volume equals length times height, or length times width times height, sorry. Length times width times height. But in this case, it's real specific. It says it is a box with a square base, right? And a square base means that your length and your width are the same. So if you look what they did here in the picture, they said if your length is x and your width is x, and then your height is h, what they're saying here is your volume would be length times width times height would be x squared times h in this case. So that's our primary equation that we're trying to maximize. We're trying to maximize the volume. What's the issue with this is our volume is in terms of two variables, and we can't handle it when it's in terms of two variables. So what we need to do is get this in terms of one variable. So how do we get it in terms of one variable? We have to look at the restrictions. Well, what's the restriction on this case? The restriction on this is that you can have a surface area of 108 square meters. So we need to figure out the surface area of the picture of this box. And if you look, they actually cheated and gave it to us, but I want to make sure you understand how the heck they got this. So let's think about the base of this. The base of this would have an area of x times x, which would be x squared, so that's where the first one is. And then think about the fronts, the sides, the front, and the back. Those would all be the length or width, which is x, times the height, which is h. So each one of those four faces would have an area of xh. So when I add those four together, I would have 4xh. So the surface area, which would be the bottom area, x squared, plus the four sides, which is 4xh, we know that has to equal, is restricted to using 108 inches, square inches of materials. So my materials is my restrictions, and volume is what I want to maximize. So what do I do at this point? What I do at this point is I need to solve for one of the variables in terms of the other. So in this case, because we have an x squared in this one, man, I'm going to solve for h. I think h would be the easiest thing to solve for. So to solve for h, I'm going to subtract x squared from both sides. I have 4xh equals negative x squared plus 108. And then I'm going to divide everything by 4x, and I'm going to have h equals negative x squared plus 108 all over 4x. Or if you want to simplify that, I don't know if that, just go ahead and leave it like that. I mean, you could separate it and simplify it. I mean, I guess, why not? So this would be negative x squared over 4x, which would be what? Negative x over 4. And then 108 over 4x, which would be what? Plus, well, 108 divided by 4. Let me do that real quick. Divided by 4 is, one sec. 4 is 27. So that'd be 27 over x. So that's what I'm getting h to be, is negative x over 4 plus 27 over x. So what's the idea now? Now I can take this, what I have h is, and I can plug that back into my original equation. So my original equation, which was volume, is going to be equal to x squared times what we got for h, which was negative x over 4 plus 27 all over x. If I distribute that out, my volume would then be, what would that be? Negative x cubed over 4, or negative 1/4 times x cubed, that's fine. Plus, well, 27x squared over x would be 27x. So there's my volume equation that I want to maximize. Now it's in terms of one variable, which means all I have to do now to maximize it is the first derivative or the second derivative test. So let's go ahead and find the derivative. The derivative would be negative 1/4 times 3x squared. So that'd be negative 3/4 x squared plus the derivative of 27x is simply 27. Set that equal to 0. Let's go ahead and solve. Subtract 27 from both sides. So this would be negative 3/4 x squared equals 27. Multiply both sides by 4. This would be negative 3x squared equals... Oh, sorry, that should be a negative 27, right? Just wanted to be careful there. Be very, very careful. So this would be a negative 108. Divide both sides by 3. So 108 divided by 3, or negative 108 divided by negative 3 is the number 36. Nice. Take the square root of both sides, and remember plus or minus. You would have x equals plus or minus 6, but remember x is a length here. Negative 6 means nothing to us. Doesn't make any sense for the problem, so all we care about is x equals 6. So x equals 6 is my critical value. I have not proven that this is a maximum or a minimum yet. So I do need to prove it's a maximum or a minimum, and in this case I want to prove it's a max. And to prove it's a maximum, I need to do the first derivative test or the second derivative test. Note that I do have a restricted domain here. I have a restricted domain starting at x equals 0 all the way up to x equals, well, it would have to be, I don't know, you have two x's there, so x squared, whatever the square root of 108 is. But you do have a restricted domain, and just make sure you know that you don't have to test every number if you do the first derivative test. But I'm not going to lie, this is really easy to find the second derivative of, so I'm going to do the second derivative test. So the second derivative of this would be negative 3/4 times 2x, so that'd be negative 3/2 x. And then it's plus 27 equals 0, right? So that'd be equal to 0, or sorry, plus 20, the derivative of 27 equals 0. So negative 3/2 x is my second derivative. If I plug in my critical value, which is 6, this would be negative 3/2 times 6, which is a negative number. So that means when I plug the critical value into my second derivative, I get negative. That means it's concave down at that point. Because it's concave down at that point, that critical value via the second derivative test means that it's a maximum. So I have proven that it's a maximum. Okay? Now I need to interpret what the heck did the actual question want. It said what dimensions of the box will maximize the volume. So for dimensions, I need to know the x and the h value. We just found the x value is 6. How do I find the h value? Well, to find the h value, I'm just going to plug it into where I had it. So this would be negative 6 over 4 plus 27 over 6. So let's see what h is here. Negative 6 divided by 4 plus 27 divided by 6. That's the number 3 when you do that. So my h would be 3, and then we want to use units. It was square inches, so I know each one of these has to be in a measurement of inches. So if I have a restriction of creating a box with no top, and I want that box with no top to use no more than 108 square inches of material, and I want to maximize my volume that that box can hold, I have to make that box, and that box has a square base. That box would be 6 inches by 6 inches by 3 inches. Those are the exact dimensions to maximize the volume of that box with the restrictions on the amount of material we could use. So how the heck did we do that again? We started off with the original equation, realizing that it had two variables. We used a restriction to solve for one of the variables, plugged it in, so now we had our original, the one we wanted to maximize or minimize in terms of one variable, found the derivative, found the critical values, used the second derivative test to prove that that critical value is a maximum, then interpreted the answer. So that is our process, exactly as written above for each one of these problems.